let's see here. We have specific latent heat of, okay, this word, let's change it to fusion. Specific latent heat of fusion. Fusion is more commonly used. So what is that? Energy required per unit mass of a substance to change from solid to liquid phase. So you may think of melting without any change in temperature. So imagine that during melting process, temperature remain the same. So the heat is used to break down the intermolecular forces. So that heat is called specific latent heat of fusion. So it works for melting, and if it is the other way around, maybe you think of freezing, where liquid phase change to solid phase. So for freezing, we still use the same word, specific latent heat of fusion. Okay, we are still using that. Okay, so no matter melting or freezing, we use specific latent heat of fusion. The only difference is, during melting, right? During melting, heat is absorbed. So it's an endothermic process. But during freezing, heat is released, which is an exothermic process. But when you want to count the heat required, we are using specific latent heat of fusion. Okay, so of course there's a formula. The formula is here. So no matter latent heat of fusion or vaporization that we are going to learn later. Okay, so the formula is energy over mass. Energy over mass. So the definition here is based on the formula actually. Energy required per unit mass. So that's why energy per mass to get per unit mass. So that's the formula. Okay, fusion or melting or freezing, same formula. Okay, so the difference is for melting, we need to, once you get your E, right? So your E is a positive value. For freezing, once you count and get your E is a negative value. Okay. Now, sometimes we also need to know that the energy here, which is the heat energy is also equal to power multiplied with time. Power multiplied with time. This is very useful for electric device where they give you the power and how long they use. Okay, so then you just take the power in watt, multiply with time in second, and then you get the heat energy as well. Okay, so let's see the next one. Specific latent heat of vaporization, energy required per unit mass. So you see the starting is the same, same definition of a substance to change from liquid to gas phase without any change in temperature. So it means this is liquid to gas. It's a boiling process. So the energy during boiling process. So likewise, if you put it in the other way around, condensation, we still able to use this formula. Okay, condensation. So again, boiling, it is endothermic, so you have to use positive. For condensation, it is exothermic. Okay, so now together with the formula that we learned before this, we have another formula actually. So that time we learned this formula. C, okay, I write it down here. C equal to E over M delta theta. So this is the formula that we learned before. This is specific heat capacity. So if I rearrange it, I will get E equal to mc delta theta. And this formula, if I rearrange it, I will get E equal to ml fusion or E equal to ml vaporization. So these two formula is used when there is no temperature change, and this formula is used when there is a temperature change. So the delta theta means change in temperature. So let's say, for example, so let's say you have a solid at X. Let's say this is temperature. Degree Celsius or Kelvin will be just fine. This is time. Okay, so you have a solid at temperature X degree Celsius. So you heat it up. Then it melts. It will become flat for a short period of time as the melting process happens without change in temperature. And then it become liquid, and the temperature of liquid increases, and then the liquid boil, and then after that it become gas, so the gas increase in temperature again. Okay, so in this situation, right, so this is formula 1, let's say, this is formula 2, this is formula 3. Okay, so when should we use which formula? Okay, so during the first process, yeah, the first process, you heat up the solid, there is a change in temperature, so we use formula 1. So during this process, where we have the melting of the solid, for the melting of the solid, there is no temperature change, so we use number 2. This is latent heat of fusion. Okay, then we continue. So melting finish, the liquid heat up. There is a change in temperature, so we use formula 1. And when the liquid reach the boiling point, it boils, and there is no change in temperature. So in this situation, we use formula 3. And the liquid finish boiling, and it becomes gas. So the gas continue to heat up. So there is a change in temperature. So we use formula 1. So likewise, if the vapor cool down, so you will have something like this, the cooling process. Okay, so similar actually. So the gas cool down. Okay, cool down. So there is a change in temperature. We use formula 1. And now this point onwards is where the gas condenses. The gas condenses into liquid. So this process involves no change in temperature. So we use formula 3, latent heat of vaporization. And then after that, this part, the liquid cool down, change in temperature. So we use formula 1. And this part, freezing of the liquids to become solid, no change in temperature, we use formula 2. And finally, this part, the solid cool down, so there is a change in temperature, so we use formula 1. So I hope you see some general concept. When there is a change in temperature, we use E equal to mc delta theta. So if there is no change in temperature, we use ml fusions for melting and freezing, and we use ml vaporizations for boiling and condensations. So I have to be careful with that. Okay, so let's move on first. Yeah, specific latent heat of vaporization always greater than that of fusions for a given substance because. So that means they are trying to say that this is greater than this. Why? During vaporization, greater increase in volume than in fusion. So when I say greater increase in volume, so you have to know that the work done is pressure multiplied with change of volume. Okay, so I just add it here. Think of this formula. W equal to pressure multiplied with change in volume. So when there is an increase in volume, in big amount actually, during vaporization, the volume increase a lot. So if the volume increase a lot, then the work done will be a lot. So thus, more work done against atmosphere. Okay, because volume increase a lot during vaporization. But during melting, the volume increase a little bit. So the work done is a little bit also, and because of that, less energy required. In vaporization, particle needs to be separated further apart than in fusions. So more work is done against forces of attractions when vaporizing. So you see they are talking in another aspect. So this is the internal energy. Okay, internal energy. This is to overcome the internal energy. And internal energy increase, in other words. Okay. And this is the work done. This is the internal energy. So two different aspects. Now let's move on. Determining specific, okay, typo error. Specific latent heat of vaporization. LV. Okay. Now let's see how we do it. You want to find the LV, right? So basically you have to do E over M. So we need to know the energy, we need to know the mass. The mass is the mass of liquid. So the mass of liquid that vaporize actually. Okay, so now here, quantities required, mass at time intervals. So imagine your apparatus is set up in this way. You have liquid in the container. You heat up the liquid. You heat up the water. So of course, initially you write down the mass. So when you heat up the water, so you should expect, or maybe I should put it in this way. You have to heat up the water until it reaches 100 degrees Celsius. It must reach 100 degrees Celsius. That means you have to heat it up until it boils first. It boils. And then our timing starts and the experiment start at boiling point. Okay, at boiling point. So of course it is kind of common sense to know about this because we are determining specific latent heat of vaporization. As you can see, specific latent heat of vaporization happens during here. During here, this is specific latent heat of vaporization that involve. So don't include this part. Heating up the liquid is related to specific heat capacity. So we don't want to involve this part. We want these alone. So we have to heat the liquid until 100 degrees Celsius. Then we start the timing. Okay, so that's how you can see here. Beaker, sorry. Okay, so here. Beaker containing water heated to 100 degrees Celsius and maintain at 100 degrees Celsius. Okay, at this time, you start looking at the mass of the water and you start your time. at regular time interval. That means it's like every 1 minute, for example, every 1 minute you read the mass of water that remains here. Okay, so plot graph of mass m against time t. So you should expect a graph like this. Mass, this is mass remaining, mass of waters remain against time. So since you are heating it up, so you should expect the water keep boiling and change to steam. So the mass of water that remains will keep going down. Keep going down. So, but the thing is, the quantities required over here, where they said mass at time interval, is not the mass of water that remain. It's the mass of water that vaporize. So we have to minus. Imagine that you take the initial mass of water. The initial mass is the mass when it reaches 100 degrees Celsius. That is the initial mass. You minus with the water remains, then you will get the mass of water that vaporize. Okay, the mass here is mass of water that vaporize. Okay, so it should be like this. Okay, they should have more and more water that vaporize along the way. Now we want this mass actually. Okay. What other quantity that are required here is the voltage and current. So as you should be able to know that power is equal to voltage times current. So that's why we need this quantity to get the power. Okay. So to get the power, so you should have the voltmeter that connect to the electric heater, and you should have the ammeter that connect to the circuit over here as well. So if numerator and denominator in latent heat equation divided by time. So imagine we are talking about this formula now. So you divide by time at the numerator and the denominator. So you have E over delta T and you have M over delta T. So the formula look like this. It's something like this. Initially, it is LV equal to E over mass. Then you divide by time and divide by time. Then you get this. So why we have to divide by time? The reason is quite obvious. The when you take E divide by time, right? Then you will get the power supplied P, and that means it become P over delta M over delta T, and P is VI. During the experiment we are controlling the voltage and the current, so we have the value, so we can substitute inside and get the power, and the numerator settle, and the denominator we have to know that delta M over delta T, which is this one, this graph. So imagine we are finding the gradient. So the gradient is change of mass over change of time. So you will get that from the graph. Okay, from the graph. So we have to use positive. Use positive means we are considering this, not this one. This is negative gradient. So at the bottom, we will have the gradient at the end. So this is the gradient at the bottom. Then let's see here, replacing quantities in original equations. So LV equal to power over gradient. So power over gradient. power over gradient, or Vi over gradient. Substitute values, rearrange and solve, then at the end you will get latent heat of vaporizations. Okay, so this is about the experiment to get latent heat of vaporization. Now let's move on to the other side. Okay, on this side, we have past year questions to go through. So this question, let's take a look. To harden a sample of pure gold, silver is mixed. So they are trying to do alloy. Alloy is where they mix the different kind of metals. So that mixtures contains 5.0% silver by weight. 5%. So the initial temperature of the silver is 27 degrees Celsius. The room temperature, no, it's around room temperature. Calculate the initial temperature of gold so that the final mixtures is at the melting point of gold. Okay, so let's think about it in this way. So you have a container that has gold. Okay, so gold is here. Gold. Let's say, for example, 95 gram. Example only lah. They don't mention what kind of mass is using. So I put 95 gram because I want to make my calculation easier. As they said here, they use 5% silver by weight. So that means 95% is gold. So I set my mass as 95%, then I will be very convenient in my calculation. So now I add silver. Silver at 27 degrees Celsius is solid. So I add 5 gram. 27 degrees Celsius. So you add inside into the 95%, 95 gram of gold. So what is the temperature of this? Don't know. The initial temperature. So I call it theta initial. Okay, then according to the questions, so they said at the last part, so that the final mixtures is at the melting point of gold. Okay, so melting point of gold, 1340. 1340. Okay, so final 1340 Kelvin. Oh, this is Kelvin. So if that is the case, let's change everything to Kelvin then. Okay, so this is 27 degrees Celsius. 27 plus 273 equal to 300 Kelvin. Okay, 300 Kelvin, and at the end you have to reach 1340 Kelvin. So this one have to reach 1340 Kelvin as well, which is the melting point of gold. Okay, so now let's consider silver alone. Consider silver alone. Silver alone start from 27 degrees Celsius, which is a solid. So this graph is applicable. This graph is applicable. Let's us recycle the graph. Okay, so if you, okay, let's say for this case, 27 degrees Celsius for the silver. And you heat up the solid. Because you put inside, this should be very hot. This should be very hot. About what temperature is this gold now? Okay, so how to predict? It should be higher than 1340 Kelvin. This one should be higher than 1340 Kelvin. Okay, so should be higher. Okay, let's say I change my situation to Kelvin since the whole question is using Kelvin. Okay, I change it to Kelvin, and I have to say that X is greater than 1340 Kelvin. Okay, what's the reason? Because you put something cold into it, so the hot gold liquid is expected to cool down to 1340. Maybe this is 1004 or 1005. Then it cooled down to 1003. Okay, the heat is given to the cold silver to heat it up to 1340 from 300 Kelvin to 1340. So you need to heat it up. So the goal is heating it up. So we should expect the initial temperature of gold to be higher than 1340 so that it can heat up the silver. Okay, let's come back to silver again. 27 degrees Celsius or 300 Kelvin. So let's use Kelvin all the way. So I changed my mind. Use Kelvin. 300 Kelvin. So we heat up the the silver is heated up by the gold. So we heat it up to 1340. Where should we stop? So you see information. Melting point of silver is 1240. So that means the solid will heat it up until the melting point at 1240. So this should be 1240. Then it continues to heat up until the final temperature, which is 1340. Okay, so I just put it in blue. So heat it up, yeah, and then melt, and then to 1340. So we expect it haven't reached the boiling point yet. 1340 is just slightly higher only. 1340. So this blue color path is the process that silver goes through. So silver will go through the heating up of solid, melting, and then the heating up of liquid. 3 processes. So for silver, you have to use formula number 1 for the heating up of solid. Number 2, you have to use latent heat of fusions. And then number 1 again for this part, heating up of liquid, you have to use formula number 1. This is for the heating up of liquid, silver liquid. Okay, then how about gold? Gold will be easier a bit. Gold is just starting from a temperature that is slightly higher than 1340 we expect. So we should start from somewhere here until the melting point, then we stop already. Okay, so this is the X Kelvin that we are looking for. Then we heat it up until the melting point, and then finish. Okay, so for gold, we involve formula 1 only. Until melting point, then finish. We can switch off the heater already when they reach melting point of 1340. Okay, so now let's do the calculation. We want to look for X. Okay, so let's separate it into 2 parts. For the gold, for the silver. Okay, so the main concept here is the heat is released by gold liquid to heat up the silver solid. That means the gold is going through an exothermic process, release heat to the silver. Silver is going through endothermic process, get the heat from the gold and heat up. Okay, so for the gold, like what we discussed, it involves only formula 1. So we use E equal to mc delta theta. So the mass of gold, we already set 95. Okay, so and oh yeah, we have to use SI unit, right? So let's change it to okay, SI unit. Why we have to use kg? Because you see here, you can see the unit here. The unit here, joule per kg per Kelvin. So it's per kg. So 95 gram, you change to kg is just 0.095. So mc delta theta. C is the specific heat capacity of the gold, which is 129. 129 for the gold. 129. Delta theta, which is the change in temperature. So it's just x minus 1340. Okay, this is for gold. Okay, then settle for gold. Okay, now for silver. Okay, so let's say I just simplify it a little bit. Zero point 0.095 times 129. 12.255 x minus 1340. So this is the Q, the heat released by gold. Okay, now let's count the silver. Okay, silver. Like what we have discussed just now, silver start from 300 Kelvin and you heat it up to 1240, then melt, then the liquid heat to 1340. Okay, so we need to involve 3 processes here. Okay, so the Q or the E okay, our chapter is using E. It's just that I used the Q only. Okay, let us use E then. The E means the heat energy. Okay, so it involves 3 processes. mc delta theta. This is the heating up of the solid at 300 Kelvin until melting point. Okay, I write down first. This is 300 Kelvin to 1240 Kelvin. Okay, now it melts. The silver melt. Silver melt at 1240. So E equal to ml of fusions. So this happened during the melting at 1240 Kelvin. Okay, then after that, the process continue. Now we have the heating up of the liquid, the silver liquid. So this is for 1240 until 1340. So we have different three processes altogether. Okay, so the thing is, we have to substitute value 0.05 for the mass of silver. I set 5 gram. 5 gram divided by 1000. Divided by 1000. 0.05. 0.005. The C for silver is 235. The change in temperature 1240 minus 300. Then MLF 0.05. Latent heat of fusions 105. 105. Okay, be careful with the unit. So you see they use kilojoule here. Kilojoule. This one they use joule. This one they use kilojoule. 105. Okay, let's change to joule times 1000. 105 times 1000 kilojoule to joule. The reason is this. That's why we times 1000. And after that, it's a trap if they put like this. It's a trap. We must be very careful. Okay, then we add up with the heating up of the silver liquid. 0.0. Oops, this one the mass. The mass is 0.05. Must be the same one. Okay, so 0.005. 0.005. Okay, now the C of the silver, liquid is the same. They said it here. Solid, liquid, same only. Okay, same. So if they are the same, then we just write back 235. Then the delta theta is 1340 minus 1240. Okay, then we add up everything here. I have to just press calculator to add up. Okay, so 1747 joule. 1747 joule. Okay, so this 1747 joule is actually the heat absorbed by silver. And they're supposed to equal one. They're supposed to equal. Because the heat released by the gold is absorbed by the heat. The heat released by gold is absorbed by silver. So that's why these two must equal to each other. Okay, then we just do some calculation and find x. So I divide by 12.255, then I add 1340. So I will get 1480 Kelvin. Correct to 3 significant figure. Okay, 1480 Kelvin. So yeah, that's how we do it. Settle.